Well, hello, welcome again to our journey into algebra and number theory, and we've been looking at the Gaussian integers. These are all numbers of the form a plus ib, where a and b are ordinary integers and I squared is minus 1. And we've seen how we can develop a division algorithm for these Gaussian integers. They form a ring. We've got a division algorithm, and we also have a version of the Euclidean algorithm and a notion of ideals, which we've defined. So our next theorem was theorem 4, which was to prove that every ideal in the Gaussian integers is principal, just as we saw a similar result in the ordinary integers. The proof is very similar to what we saw before in the case of the ordinary integers. So we let I be an ideal. If I is trivial, then there's nothing to do. It's already principal. If not, then we can choose an element alpha in this ideal of smallest positive norm. This won't be unique, but there will be at least one of these of smallest positive norm. Now, as I said, unlike the case of integers, this is not necessarily unique. So as before, I claim that this ideal is generated by this alpha that we've chosen of smallest positive norm. If you've got any other beta in the ideal, then I can simply apply the division algorithm and write beta. So I divide beta by alpha, and we have a Q and R, which are Gaussian integers, with the norm of R strictly less than the norm of alpha. But then I can make R the subject of this, so R is beta minus Qi, and this, because we're in an ideal, this belongs to the ideal as well. So R belongs to I, and by the minimality of the norm of alpha, then if the norm of R is less than that, the only thing is the norm of R must be 0, and hence R is 0. And that means that my beta is in fact just a multiple of alpha, which tells me the ideal is generated by alpha. Now, we'd like an analogue of the Bezout identities, and that is, if we take two Gaussian integers, then we'd like to take their GCD and write the GCD as a Gaussian integer linear combination of the two numbers alpha and beta we started with. That is, the ideal generated by alpha and beta is generated by the GCD of these two, and that means, of course, then the GCD is just a Gaussian integer linear combination of the two we started with. The proof's fairly simple. If we take alpha and beta and we take the ideal generated by those, so this is an ideal, so it's principal. It must have a generator. I call that epsilon in the Gaussian integers. And then epsilon has to divide alpha. Epsilon divides beta, as in the proof of theorem 4. And that means that epsilon then is a linear combination of these two for some gamma and delta in the Gaussian integers. And then any other divisor of alpha and beta from here has to also divide epsilon. And that is sufficient to prove the result. Just as an example, we'll calculate the ideal of these two. So I've done that in a separate page here. So I take these two Gaussian integers. I'm going to divide this one by this one. And so I multiply top and bottom by the conjugate here to realize the denominator. Simplify gives me this. Now 17 goes into 34 exactly twice, and 17 into 18 goes once, remainder of 1 and 17. So again, I split this up into 2 plus I, and then the quotient here, the I on 17. So the difference between these two is less than a half. Now I then put R to be equal to my 5 plus 7i minus what I'm dividing by and times the quotient, and that'll get me the remainder. So I simplified all that, and out comes minus 1 minus I, and we just check that the norm of R is 2, and the norm of 4 plus 2i is 16 plus 2 is 18, and that's less than that, as it has to be. So that tells me then that the GCD of the two numbers I started with is the same as the GCD of 4 plus 2i and minus 1 minus I. I now again continue the algorithm, so I divide this by this one, again multiply by conjugates, simplify, I get this. Now in this case this goes into this exactly, so there's no remainder. So the last non-zero remainder in the division algorithm was minus 1 minus I, and that's going to be a GCD. But of course we could multiply everything through by a unit. If I choose the unit minus 1, for example, I might get 1 plus I as a GCD. And that's what I wrote in the notes here, that the answer is 1 plus I, or any unit multiplied by this number. Now, Theorem 4 can also, from Theorem 4, we can also show this following very useful, very important fact about Gaussian primes. Now, in the ordinary integers, any prime which divides a product must divide at least one of the factors. And we have an analogue here. If pi is a Gaussian prime and pi divides alpha beta in Zi, then pi must divide alpha or pi must divide beta. Now the proof's very similar to the one we saw in the ordinary integers. We take pi, if pi doesn't divide alpha, so if pi does divide alpha, we're finished. If it doesn't divide alpha, then the GCD of pi and alpha is a unit. So by Theorem 5, we can write that unit as a Gaussian integer linear combination of alpha and pi for some x and y in the Gaussian integers. Multiplying through by beta, we get this expression here. And now we note that pi, by assumption, pi divides alpha beta, so pi divides this term, so pi is going to divide beta times alpha. So pi divides beta alpha, so that means that beta alpha is some multiple of pi for some gamma in the Gaussian integers. Now epsilon's a unit, so I can take its inverse on the other side, and that now says that, and these are all Gaussian integers, so pi divides this right hand side, so pi divides beta. Now from the above it can be shown that any Gaussian integer can be factorized into Gaussian prime factors, and that this is unique up to order and multiplication, as you might expect by a unit, just like the ordinary integers. So for example, we can take 5 and factor it as 2 plus I, 2 minus I, or we could multiply this by the unit I, and then we'd have to multiply this by the unit minus I, and that would give me this expression. So the factorizations look different, but they only actually differ by a unit. You might like to compare this with saying that 6 is 3 times 2, but it's also minus 3 times minus 2. Now you'll recall the earlier comments to the effect that this is the exception rather than the rule in rings of this form. Generally, rings of this form, the factorization is not unique, but happily in the Gaussian integers it is. Now returning to our original aim of discussing which numbers can be written as the sum of two squares, we now have the following lovely theorem. It says that if p is an odd prime, this is an ordinary prime, then the following are equivalent. P is 3 mod 4, so if you've got a 3 mod 4, suppose p is a 3 mod 4 prime, then p cannot be written as the sum of two squares, and p, and that's equivalent to, p is a Gaussian prime. So these all are equivalent to each other. So if I give you just an ordinary 3 mod 4 prime, then it is a Gaussian prime. So for example 7 is a Gaussian prime, and 7, as we saw, cannot be written as the sum of two squares. Now the proof takes a few steps here, so we'll start off by supposing 1 is true, that is p is a 3 mod 4 prime. and we're going to assume that you can write p as a sum of two squares and get a contradiction. Now that means a squared plus b squared is 3 mod 4, but the only squares in Z4 are 0 and 1, and so the only sums you can get here will be 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 2, you don't get 3, so that's a contradiction. So p is not the sum of two squares, and so that proves that statement 1 implies statement 2. Now we're going to suppose that p cannot be written as the sum of two squares, and I'm going to suppose that I have got a factorization in the Gaussian integers of p. Well, we can take norms then of both sides and use our properties of norms. Now the norm of p is p squared, and if I take alpha as a plus ib, beta as c plus id, then I get p squared as a squared plus b squared times c squared plus d squared. Now we're back in the ordinary integers again. So p is prime, so p divides a product, then you either have this is p and this is p, or you have so you either have a squared plus b squared is p, or this is 1, or this is 1, or this is p. Now p is not the sum of two squares by assumption, so alpha and beta is a unit in this case, because the only way that this can be true is that if alpha and beta are, or if alpha's plus or minus 1, b's plus or minus 1, and similarly with the others. And so in this case alpha or beta is a unit, and so that means p is a Gaussian prime. And that shows that if p cannot be written as the sum of two squares, then p is a Gaussian prime. And finally, to close off the loop, we suppose 3, so p is a Gaussian prime. If p is 1 mod 4, then we've seen before that minus 1 is a square root, has a square root, x, say, in Zp. That is, x squared plus 1 is 0 mod p. That means p divides x squared plus 1. Now I can factorize this in the Gaussian integers. So that says p divides these two. That means p divides that one or this one. And that tells me that x plus I is some Gaussian integer multiple of p. Or x minus I is a Gaussian integer multiple of p. And in either case, when I multiply this out, I get pb is either plus or minus 1. That's impossible. So that means p is 3 mod 4. So we can now completely characterize which integers can be expressed as the sum of two squares. So given an integer n, we write n as, we take all the 2's out, and we then take any square factor out, and we're left with b, where b is square-free integer. So this is an ordinary integer n. Now epsilon is either 0 or 1. So we take out 2, we take out possibly, if there is no 2 in it, it's not a square, then epsilon would be 0. We take out the square factor, we're left with that, and then we factorize b as a product of primes, where pi are odd primes. So the main result then is, if we take an ordinary integer n and we write it in this form, then n is the sum of two integer squares if and only if all of these pi's are congruent to 1 mod 4. All of the factors of this b have to be congruent to 1 modulo 4. Now the proof of this goes as follows. So suppose we have n as the sum of two squares. We put the GCD of these two as b. Now the n then is bx squared plus by squared. and that's going to be b squared into x squared plus y squared, where the GCD of x and y now is 1. Now let c to be x squared plus y squared, and suppose that c has a prime factor p congruent to 3 mod 4. Then that gives me x squared plus y squared is 0 mod p. b does not divide y, since if it did then p divides x, and so the GCD of x and y is not 1, which is false. So I can multiply here by y inverse squared, and I get x squared y squared all inverse is minus 1 mod 4. This means that the Legendre symbol minus 1 over p is 1, but then p is 1 mod 4, which is a contradiction. So note that if x and y are both odd, then there will be a single power of 2 as a factor of that. But we can write 2 as the norm of 1 plus alpha, so we can apply the methods of norms to incorporate this into the sum of squares. Conversely, if each of the pi's are congruent to 1 mod 4, then by theorem 7 each is the sum of 2 squares, and applying that method of norms we saw before, we have that n is the sum of 2 squares. Now observe that this proof is non-constructive. It tells us when, but not how, an integer n can be written as a sum of squares, so some trial and error is involved. So as an example, we take n to be this number, 1170. So we take out one lot of 2, and we take out the square factor 9, and we're left with 5 and 13. Now both of these are 1 mod 4 primes, so n is the sum of 2 squares. So what we do then is we write this as 3 squared, we'll keep that there. 2 is the norm of 1 plus I. We can write 5 as the norm of, say, 1 plus 2i, and 13 is the norm of 2 plus 3i, and again there's choices here as to what for all of these there are choices. We can multiply then these three Gaussian integers to get minus 11 plus 3i, and that norm then is 11 squared plus 3 squared, and then we can multiply the 3 in, we get 33 squared plus 9 squared. Now of course there are many other ways of doing this. We could have chosen 1 minus I, we could have chosen 2 plus I here, or 3 plus 2i, and I invite you to try those and find some other representations of this number as a sum of 2 squares. On the other hand, if we take n to be 792, we take out a 2, take out the square factor, I get 11, and 11 is not a 1 mod 4 prime, so this number is not the sum of 2 squares because 11 is 3 mod 4. Well, in the next recording we'll have a look at trying to decide exactly which Gaussian integers are in fact Gaussian primes, and we'll have a nice theorem that will pin that down precisely.